All right, so this is the chapter on solutions where we're going to first identify the solute and the solvent in a solution, which you may already know what solute and solvent are, and then describe the formation of a solution. All right, so what's a solute?
Something that dissolves in water.
The substance that dissolves in water and the substance that's present in the smaller quantity. So solvent is the substance that's present in the larger quantity, and the solute and the solvent together make the solution. Solutions are homogeneous mixtures of two or more substances. Remember we used the word homogeneous before in the very beginning, in chapter 3 maybe. A homogeneous mixture, that means what? If you have a homogeneous mixture, you have, when you dissolve the substance in water, like salt dissolved in water, you don't see any particles, so that's completely gone. You have a clear solution, then it's called homogeneous. They contain a solute, usually in smaller quantity, and uniformly dispersed in another substance called the solvent, usually present in greater quantity. Solutes are not visible and cannot be separated by filtration. If you all remember the lab that we did, separation by solubility, we were able to filter the sand that was dissolved in the salt water because the sand did not dissolve and did not make a homogeneous mixture when put together with the salt and water. A solute that's gone, it's dissolved in water, you can't separate using filtration. It can, however, be separated by using evaporation, because if you have sodium chloride dissolved in water, you can evaporate the water and you get your salt back. And it can give color to a solution. Now, if you remember in your little baskets over there, you have the solutions that we've been working with to do common ions, for example, looking at the reactions. Some of those solutions were blue, and that was because the solute in there, the copper sulfate, dissolved in water and gave you the blue solution. The solutes and solvents in solutions can be solids, liquids, or gases. So you can have different kinds of solution. You can have a gas solution where you have a gas dissolved in a gas. For example, air, the primary solute is oxygen, and then the solvent is nitrogen. Because you have nitrogen in larger quantity. About 70% of air is nitrogen, and 21% is oxygen. So since oxygen is present in the smaller quantity, you would call the oxygen would be the solute. There are other solutes also. That's why they're using the word primary solute. You have other trace gases like carbon dioxide, monoxide, sulfur dioxide, and other pollutants that might be in the air. Liquid solutions can be a gas in a liquid solution. Example would be soda water, where you have managed to bubble carbon dioxide, get carbon dioxide to dissolve in water under pressure. And that's what you find in all sodas. If you heat up the soda, then the carbon dioxide is going to bubble out. Primary solute there would be carbon dioxide gas, and the solvent is water. Household ammonia is another example of ammonia gas dissolved in water. Liquid in liquid would be vinegar, acetic acid dissolved in water. When you have vinegar, if you look at the vinegar bottle, at the back it's going to say 5% acetic acid. So that's why, because you have 5% acetic acid in water. Seawater is solid in a liquid where you would have sodium chloride dissolved in water. A tincture of iodine is the solid iodine dissolved in ethanol, which is the liquid there. And ethanol is alcohol, by the way. Then you can have solid solutions. Brass is an example of a solid solution. And what's the word we use for brass? Brass is a what? Is a mixture of metals, and it's called an alloy. So you have zinc solid and copper solid put together. You could call it a mixture or a solution. And then steel is similarly also where you have carbon solid and iron solid. Both are solids in that solution. Water is the most common solvent, and it's a polar molecule, forms hydrogen bonds between molecules. Okay, now it's time to go to the board. Polar molecule, did we ever talk about polar molecules in here?
We did in biology.
Like briefly.
Briefly, okay. So you have water. Water, what kind of bond does water have?
Double. The hydrogen.
No, is it ionic or covalent? Covalent, good. You have, here's a water molecule, and then which of these two elements do you think wants electrons? Oxygen or hydrogen, based on what we learned from the periodic table. Oxygen. Remember, oxygen is over on this side. These elements over here do what? They gain electrons. So oxygen is going to there's two electrons being shared here, one from the hydrogen and one from the oxygen. And oxygen is going to try to keep these near to itself. So the two electrons are going to be sort of right there. And because the electrons are negatively charged, oxygen is going to end up getting a slight negative charge. It's shown with a little delta sign. That means it's a partial negative sign, and it's not the same kind of negative sign that chloride would have, for example, because it took up an electron completely from some other metal. Hydrogen being less electronegative, meaning does not want to have electrons near it, is going to end up with a positive charge. So this is called polarity, or water is a polar molecule because it has charge separation where one end is positive, the other end is slightly negative, like a magnet. A magnet has a negative and a positive end, so does a water molecule. A magnet is called polar, and a water molecule is also called polar. Here's another water molecule, slight negative end, positive end. And since negatives and positives attract, you're going to have a weak bond or an attraction develop between the positive end of one water molecule and the negative end of another water molecule sitting right next to it. And there's going to be another water molecule right there, and you're going to have similar weak bonds, and those weak bonds are called hydrogen bonds. And these hydrogen bonds behave like the water molecules are holding hands. That's why the water molecules want to stick together, and you have to heat water up to a high temperature like 100 degrees Celsius in order for the water molecules to break away from the surface and evaporate, because you have this attraction between the water molecules. So any questions on this before we go on? So water is a polar molecule, forms hydrogen bonds between molecules. There they are. And then you have the partial negative and the partial positive charge. Sodium and chloride ions on the surface of the sodium chloride crystal are attracted to polar water molecules. So you have these water molecules, and then of course you have the sodium chloride. What's going to happen? If you had you dissolve the sodium chloride in the water. That's the sodium ion. The oxygen end of the water molecule is going to try to be near the sodium. So this is what you end up getting. The sodium ion gets hydrated where the oxygen end faces it, and then the chloride would be near the hydrogen. Another hydrogen. So the chlorides get surrounded by the positive ends of the water molecule, and the sodiums get surrounded by the negative end of the water molecule. And this process is called hydration. So on the surface of the sodium chloride crystal, sodium and chloride ions on the surface of the sodium chloride crystal are attracted to the polar water molecules. In solution are hydrated by water molecules that surround each ion. So all this is based on the negatives attracting the positives. Like that sodium, for example, the purples in the drawing are sodiums, and they are both going to be surrounded by the oxygen ends. Whereas the greens are the chlorides, and the hydrogen ends of the water molecules are going to be facing them. And there it is at the bottom drawn once again. The reds are facing the sodium because the red is the oxygen end. The white ends are facing the chloride because the whites are the hydrogen ends. Attractive forces occur between solute and solvent particles when the solute and solvent are similar in polarity. So both of these are polar molecules. The sodium chloride is polar, and the water is polar. And then because of the negatives, they both have negative and positive ends, so there's going to be attractive forces. The expression like dissolves like describes the common polarities of the solute and the solvent particles needed to form a solution. So when do you make a solution? When you have two polar substances, they're both going to attract each other because they both have charged ends, and they will make a solution. If one of these was not polar, then you're not going to form a solution. Like example would be oil and water. Oil is not polar, does not have negative and positive ends, so you put it together with water, there's not going to be this kind of attraction, and you're not going to be able to dissolve the oil in the water. They're going to form separate layers, and they won't mix. And that's where the expression like dissolves like comes from. If you have two polar compounds, they will dissolve. Like dissolves like in each test tube, the lower layer is CH2Cl2 more dense, and the upper layer is water. So this is a hydrocarbon. It's not polar, and water is polar, and the two layers don't mix. So you can compare this compound to oil, for example. The nonpolar solute iodine is soluble in the nonpolar solvent. The ionic solute nickel nitrate, green, is soluble in the polar solvent. So which means if you have a polar solute, it's going to dissolve in a polar solvent. If you have a nonpolar solute, like iodine, it's going to dissolve in a nonpolar solvent. So there are some things that are nonpolar would dissolve easier in oil compared to dissolving in water. Solutions will form when you have a polar solute and a polar solvent, or if you have a nonpolar solute and a nonpolar solvent. So the nature of the solute and the solvent have to be the same. Either both have to be polar or both have to be nonpolar in order for a solution to form. And if one of them is polar and the other is nonpolar, then you're not going to form a solution. Okay. In water, a polar solvent, the hydrogen bonds provide strong solvent-solvent attractions. These are called solvent-solvent attractions. So within there you have all these attractions, and that's what we call. When sodium chloride crystals are placed in water, partially negative oxygen and atoms in water molecules attract the positive sodium ions. We already looked at this. Partially positive hydrogen atoms in other water molecules will attract the negative chloride ions. So when sodium chloride dissolves in water, the formation of solution can be written as sodium chloride breaking down into sodium and chloride ions. And this would be considered a separation of ions. So every time you dissolve a soluble salt, like this one, in water, if it's soluble, if it's not soluble, then you're not going to see this separation. It's going to stick together. And how do you decide which ones are soluble? Based on what?
Charges.
No. Remember what we looked at when we did that lab? The electrolyte lab?
This
The rules, right? Who has the rules? Nobody has the rules? I'm sure I can find 4 pages here. I don't have them. It was in your manual, yeah. We used it. Sodium chloride being a soluble salt, according to your rule, it's soluble. So it's going to do this. But if you go and find silver chloride on there, AgCl, and tell me if it's going to, when you put it in water, is it going to break down into ions?
No. It says no.
No, because according to the rules, chlorides of silver are supposed to be insoluble, right? It says all chlorides are soluble except for those of silver, lead, and what? Barium chloride? Barium chloride is soluble, barium chloride is not insoluble. So, which rule tells you this?
Number 3.
What does it say? All chlorides are
Soluble
except
those of PB, Ag, and
Hg. Okay. So those are your insoluble chloride, and silver chloride happens to be insoluble. So you can't write that kind of a dissociation reaction for silver chloride. This is called dissociation, where sodium chloride dissociates into sodium and chloride. Polar molecules such as methanol are soluble because of the polar OH group that forms hydrogen bonds with this polar solvent water. So some compounds will form hydrogen bonds, and then they would also, and because they're polar, just like water, and they would also dissolve in the polar solvent. Solutes that are nonpolar, such as iodine, oil, or grease, do not dissolve in the polar solvent water. There are no attractions between the nonpolar solute particles and the polar solvent particles. And nonpolar molecules will form a solution only with nonpolar solvents. Right, solid lithium chloride is added to water, it dissolves because the lithium ions are attracted to the oxygen atom of water or the hydrogen atom of water. The oxygen atom. The chloride ions are attracted to the
Hydrogen.
positives. Will the following solutes dissolve in water?
I don't know.
Iodine was up here. Remember on that page? Right there. And iodine is a nonpolar solute. It's soluble in the nonpolar solvent, so it's not going to be soluble in water. What about hydrochloric acid, HCl? This would dissolve in water. Sodium sulfate, how would you check about sodium sulfate? You can use those rules to check. And on the first rule, it says all salts of sodium, potassium, and ammonium are soluble. That includes sodium sulfate. So most polar and ionic solutes dissolve in water because water is a polar solvent. Okay, so let's go to the e-text and look at those problems now. We talked about electrolytes when we did our electrolyte lab. Remember? Okay. They dissolve in water, completely dissociate, break up into ions, forming a solution that conducts electricity. So would potassium iodide be a good electrolyte? This one here. Yes. What about that one? We decided this was insoluble based on the rules. We said silver chloride was insoluble. So if it's insoluble, it's not going to be able to conduct electricity because it's not breaking down into ions. When electrolytes dissolve in water, they do not oh, this mistake continues to be here. This is when non-electrolytes. Okay, so when non-electrolytes dissolve in water, they do not dissociate into ions, but break up into molecules, forming a solution that does not conduct electricity. An example here would be sugar, for example. You put sugar in water, it's going to dissolve, it's going to go away, but it has not given rise to any charged particles, and that's why it's not going to conduct electricity. In water, strong electrolytes completely dissociate, produce ions, conduct an electric current. For example, sodium chloride would break down into sodium and chloride completely, meaning there's not going to be any sodium chloride intact particle left. And same thing with calcium bromide. One calcium bromide particle would break down into one calcium and two bromides because there's two bromides in there. And both of these solutions would give you a lot of conductivity, and you'd get a really bright bulb. In water, weak electrolytes dissolve mostly as molecules, produce a few ions, conduct a weak current. So you have some substances that are weak electrolytes. Examples of those would be hydrogen fluoride, hydrofluoric acid, or ammonia. When they're put into water, most of the substance is in its intact form. That means there's very little dissociation, although you do have some hydronium ions and fluoride ions created. How do you get the hydronium ion, by the way? What's actually happening here? You have HF plus water. This water molecule is grabbing this hydrogen, and you make this hydronium particle. And then this part is left by itself. Most of the hydrogen chloride is going to be in this form. So like you might have 90% in the HF form, in the combined or in the intact form, and only 10% is going to be in this form. So since you have very few ions produced, because only a small amount of it dissociated, you're going to have weak conduction, or you have a weak electrolyte, right? And that's just the nature of the substance. Ammonia is going to do the same thing. Ammonia can put into water. It's going to take up one hydrogen from the water, and you get the ammonium ion, and then what's left of the water, the OH. And we need to kind of get used to this because we're going to see this again in acids and bases. So ammonia, put it together with water, you make the ammonium ion, where one of these hydrogens is adding on to the ammonia. And then remember, water is made up of H and OH. This goes with this, and you have OH left. So in the process, you've created two particles. Ammonium is positively charged, hydroxide is negatively charged. But then again, not all the ammonia is doing this. Some of it is doing it. If 80% does it, if 80% stays in this form, in the ammonia form, and only 20% dissociates and makes the ammonium and the hydroxide ions, then you're going to get less conductivity compared to something like sodium chloride, which dissociated completely. And so that would be a weak electrolyte. What about a non-electrolyte? Dissolves as molecules, do not produce ions, and do not conduct a current. So, for example, would be sugar. Put it in water, and it's dissolved. You don't see it anymore, but then it's not making any charged particles. And in this case, you would get no light on the bulb because it's a non-electrolyte. This that you're showing here is for the hydrogen fluoride, by the way. So you see some light over there. All right, so strong electrolyte, complete dissociation. Types of particles in the solution is going to be only ions, and it would conduct electricity. Examples of ionic compounds would be all these salts. All of these are going to be soluble. Notice you don't have silver chloride on here. Neither do you have lead chloride or barium sulfate because they're all insoluble. Then weak electrolytes, you're going to have partial dissociation, meaning some of your substance is going to dissociate. Examples would be the two that we looked at, the hydrogen fluoride and the ammonia. Mostly molecular or mostly in the molecule form, and only a few ions. It's going to conduct electricity weakly. Examples are HF, water, ammonia, and acetic acid. Non-electrolyte, there's going to be no dissociation at all. The particles in solution would be only molecules, and examples would be organic compounds such as methanol, ethanol, and urea, and sugar, which is sucrose. You will have some questions like this on mastering chemistry, by the way, this will come in handy to answer those questions, and the pages that I just gave you again. Do you have your page from before, Diamond? The page that went along, you already have yours?
No, it's in my lab manual.
Oh.
Or did we turn that in?
No, I gave it back to you. I just passed these out. I know I gave them to you before too. You should probably have one from before. Oh, here's another one. You can have this. Okay. So. No, you want to make sure you keep these handy. Don't lose them. You should have kept those from before. But if you didn't, if you lose these, you're going to have trouble on the mastering chemistry. Because you will be needing those rules to answer those questions. And you might, actually, you want to keep them the whole time because this stuff is going to be on the exam too. And you will need those rules, and you will need those, the solubility rules. So make sure you don't lose them. Complete the equation for each of the strong electrolytes. Calcium chloride would break up into the top equation or the bottom equation?
Top.
Anytime you have dissociation, that's two chloride ions, right? See that particle right there, the Cl2, chlorine, with a negative charge, is not a real particle. It's absolutely senseless. Because if you have chlorine gas, free chlorine gas, then it's gonna be, the diatomic chlorine is gonna be like this. It should not have a charge on it. You have these chloride particles with a charge, then the 2 would go up in the front as a coefficient. So anytime you're showing dissociation, and it's going to be in this form. Calcium chloride would dissociate in this. We haven't done these yet, the ionic equations, but we're getting ready to get there in a minute. So you want to remember that if you're showing dissociation, the subscript is going to go up in the front. Potassium phosphate is going to dissociate into 3 potassiums, because that's 3 right there, and 1 phosphate. What's phosphate again? So which of these two is correct, the bottom or the top? The first one. What is phosphate? Is it? So that's why it's not going to break down. Remember, what's the definition for a polyatomic ion? A group of atoms that want to stay together. They are not going to split up like this. They're always going to stick together with that negative charge or positive, whatever charge they might have. Here's another polyatomic ion right here. ammonium is a polyatomic ion. So this 4 would never come up in the front if you were showing this. The ammonium ion is going to stay intact, just like the phosphate ion. So anytime you have a polyatomic ion, don't take the 4 and put it up in the front, because that's a subscript also. When I say a subscript will go up in the front as a coefficient, that statement does not apply to a subscript that's part of a polyatomic ion. Okay, so these are the two dissociations for these two compounds. All right, so let's go ahead. We're going to start using our rules again. Define solubility, distinguish between an unsaturated and a saturated solution, and identify a salt as soluble or insoluble. Solubility is the maximum amount of solute that can dissolve in a specific amount of solvent, and it can be expressed as grams of solute per 100 grams of solvent, and which is usually water. And so grams of solute divided by 100 grams of solvent would give you the solubility of the substance. And it's usually at a specific temperature too, because if you heat the solution up, you can usually dissolve some more solute. Saturated solutions contain the maximum amount of solute that can dissolve. Have undissolved solute at the bottom of the container. That means you had 100 grams of water, and in there you started dissolving sodium chloride, and you continued to add sodium chloride until there was some solid left at the bottom, and it would no longer dissolve and go into solution. You would expect that to happen at some point, right? Okay. And these have equal rates at which the solute dissolves and crystallizes. So solute plus solvent gives you a saturated solution. The solute is dissolving, but then an equal amount is going to recrystallize, because the solvent can only keep so much solute at a given temperature. If you change the temperature, you might be able to get some more in, but then again, there's going to be a limit to that also. So saturated solution, the definition will be contain the maximum amount of solute that can dissolve, and it's going to have undissolved solute at the bottom of the container. Any questions on a saturated solution? Once again, remember, solute plus a solvent is making the solution. Solute is going to be there in the smaller quantity, solvent is going to be there in the larger quantity. So here's an unsaturated solution where you have your solvent and you have few grains of the solute, and then here's a saturated solution where you have a lot of the solute and the solute is dissolved in there, but then there is some undissolved solute that's sitting at the bottom because you have put in extra solute, and that solute is not dissolving. That's when you call it a saturated solution. It's dissolving, but it's recrystallizing back, so that's why you have the appearance of the solid is always going to be there. Solubility depends on temperature, and it increases as temperature increases for most solids, decreases as temperature increases for gases. Let's talk about gases for a minute, and then we'll look at the graph. This says solubility decreases as temperature increases for gases. Where do you usually run into this? If you have a soda can that's open, and you let it sit on your kitchen counter and let it warm up, what's going to happen? All the carbon dioxide bubbles out, evolves out. It becomes flat because temperature is rising, so the gas is no longer going to stay in the solution. And that's exactly what it says. Solubility decreases as temperature increases for gases. If you have the same soda can that's open and you put it in the fridge, then you're going to be able to keep the soda in the right form for a little bit longer. Let's look at the graph now. Here's solubility in grams per solute per 100 grams of water, and temperature is on the x-axis, increasing as you go to the right. Notice here, sodium chloride, the solubility does not change a lot. At 20 degrees Celsius, you have about 40 grams dissolving per 100 grams of water. But then at 100, you have a little more. At 20, it's a little less than 40, and at 100, it's about 40. So sodium chloride, the solubility does not change drastically as you increase temperature. But for other substances like glucose, potassium nitrate, the solubility really shoots up as you increase the temperature. You can see those graphs going up, right? Okay. At 40 degrees Celsius, the solubility of potassium bromide is 80 grams per 100 grams of water. Identify the following solutions as either saturated or unsaturated. So this is the solubility, which means at 40 degrees Celsius, you can get in 80 grams of potassium bromide in 100 grams of water. If you have 60 grams of potassium bromide added to 100 grams of water at 40 degrees Celsius, would you call that an unsaturated solution or a saturated solution? Because 80 can go in. 200 grams of potassium bromide added to 200 grams of water at 40 degrees Celsius, this would be saturated because you're going to have 20 grams sitting around. 25 grams of potassium bromide added to 50 grams of water. Okay, because it's half as much, and you still have room for 30 more grams to go in when you double the 50 grams to 100 grams. All right, Henry's law. This is one of the laws that we're going to look at in this chapter. This is the only one, actually. States that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. So you dissolve a gas in water, you're going to have some undissolved gas, and if you have that gas under pressure, then you're going to be able to dissolve more in. And that's what we see with the soda cans. Carbon dioxide is dissolved into the soda, whatever flavor it is, dissolved in there, and it's dissolved under pressure, so that's why you're able to get in a lot more carbon dioxide. At higher pressures, more gas molecules will dissolve in the water, in the liquid. When the pressure of a gas above the solution decreases, which would happen when you were to open up a soda can, then the pressure is released and the solubility of the gas in the solution will also decrease. So carbon dioxide under high pressure is what you have in here, and you have lots of carbon dioxide. It's going to stay in the liquid, in the dissolved form. You release the pressure, and the carbon dioxide will start bubbling out of the solution. And then you have fewer molecules that would stay dissolved at the lower pressure. Any questions on this before we go on? So under high pressure, you're going to be able to dissolve lots of gas, just like you have carbon dioxide in a closed can. Under low pressure, the carbon dioxide molecules bubble out, and you end up with less carbon dioxide dissolved. So solubility would decrease as the pressure is released. Why could a bottle of carbonated drink possibly burst or explode when it's left out in the hot sun? Because in the hot sun, you increase the temperature, so what's going to happen?
Increasing the gas.
The gas is going to all come out of the solution, and then that's going to make the can or the container is going to burst. Why do fish die in water that's too warm?
Because when the water gets super warm, the solubility of the salt and the water gets...
The solubility of what? Which substance?
The water, like with the salt water, like I'm saying, the salt.
What do fish need that's dissolved in water?
Air.
Oxygen.
That's
Okay.
what I'm trying to do, but I'm just saying.
Why do fish die? They die because when the water warms up, all the oxygen bubbles out. Okay. If the oxygen bubbles out, then they're not going to have any to breathe. Remember, what do fish use? They use the dissolved oxygen. The water passes over their gills, and they're able to use the oxygen that's dissolved in the water. Okay, so pressure in a bottle increases as the gas leaves the solution because it becomes less soluble at higher temperatures, and as pressure increases, the bottle would burst. Oxygen is less soluble in warm water. Fish cannot obtain the amount of oxygen required for their survival, so they're going to die. All right, now we're going to start using our rules. Ionic compounds that dissolve in water are soluble salts, and those that do not dissolve in water would be called insoluble salts. So here are some examples of insoluble salts, and these, remember, we said were also known as precipitates. This is cadmium sulfide, and we have seen precipitates like this when we did our experiments, right? We may not have seen each one of these, but we may have seen all of them. So these are insoluble salts that make these precipitates, and they will all this orange stuff is going to eventually settle to the bottom as a solid. Soluble salts typically contain at least one ion from groups 1A, or nitrate, or an acetate. This is the same set of rules that I passed out to you. It's in a different form. So, and this is so you can use this chart also if you wanted to decide which salts are soluble and which are insoluble. So if it contains lithium, sodium, and potassium ions, then it's soluble. If it contains ammonium, it's soluble. Nitrate, acetate, chloride, bromide, and iodide are soluble, except for silver, lead, and mercury. Sulfates are mostly soluble except for barium, lead, calcium, strontium. Carbonates are insoluble. Sulfides, phosphates, and hydroxides are insoluble. The chart that I gave you is a lot more detailed, so you would prefer to use that chart. All right, so potassium sulfide is an ionic compound soluble in water based on the rules, because potassium, sodium, and ammonium salts are soluble. And the reasoning would be it contains potassium ions, because the first rule, even on your chart, says what? All sodium, potassium, ammonium salts are soluble. Calcium nitrate is soluble in water, contains, because all nitrates are soluble. Lead chloride is insoluble because all chlorides are soluble except for those of lead, silver, and mercury. That's your third rule. Sodium hydroxide, if it contains sodium, then it's soluble. Aluminum phosphate is insoluble. What rule is this? Where would you find phosphate on your list of rules? Go and look on your rules. It's way down the bottom, I think. Which mentions a whole bunch of anions and then says they're insoluble. So only phosphate that would be soluble would be those of sodium, potassium, and ammonium, based on rule 1. I predicted the following compounds are soluble in water. Lithium phosphate. Go and look at your list.
Oh, I'm sorry.
Lithium phosphate would be insoluble or soluble?
Soluble.
Okay, because your rule 1 says what? Lithium, sodium, potassium, and ammonium salts are soluble. Do you have lithium on your rule 1, by the way?
No.
You don't, right? You should add that to it. And lithium is just like sodium because it's in group 1, so it's going to basically be the same.
Isn't it like everything in group 1?
Right, is going to have soluble salts, but since it's not there, either you want to remember it or add it. What about lead sulfate?
No.
It's not going to be soluble. Calcium nitrate,
Soluble.
all nitrates are soluble. Silver chloride,
No, not so.
insoluble. Okay, a chemical equation shows the complete formulas of all the compounds in a reaction, like this one, for example. Lead nitrate reacting with sodium chloride, and then you get lead chloride is the precipitate there. That's why it has a little S on it, because it's in the solid form. And then sodium nitrate is the other compound. So what kind of reaction is this?
Double replacement.
Double replacement. An ionic equation that we can write, this here equation can be written out as a complete ionic equation where everything is going to show up as ions. So lead, the two nitrates that you have here, see the two outside the parentheses, that's going to show up as a coefficient. And then there's 2 sodiums, that 2 right there, and that 2 applies to the chlorides, so 2 sodiums and 2 chlorides. And on the right-hand side of the arrow, you're going to show only the lead chloride in the combined form with a complete formula, in the undissociated form, because lead chloride does not dissociate. It's an insoluble salt. The other 2 ions that would be the sodium nitrate will be shown in the dissociated form. Now here, the substances that are seen on both sides, or the ions that show up on both sides, would be the nitrate, right? Nitrate on the left, nitrate on the right. Sodium on the left and sodium on the right. Let me write this on the board so we can talk about one more thing and then we'll go on. We have lead, 2 plus 2 nitrates, 2 sodiums, 2 Cl. And you, when you're entering these into Mastering Chemistry, you have to have your charge, you have to have your AQ and your solid and liquid, whatever form it's in. If you miss anything, then it's going to mark it wrong. Okay, so things that are in the ionic form on both sides, like the 2 nitrates on the left and the 2 nitrates on the right, 2 sodiums on the left and 2 sodiums on the right. This is Cl2. Are called the spectator ions because they do nothing. And you'll run into this word on Mastering Chemistry. For some reason, it's not on the PowerPoint. Spectator ions, because they're called spectator ions because they are not making anything new. The lead chloride is being formed. So you want to write that word down and remember it, because when you're doing your homework, you're going to need it. And the lead and the chloride ions combine to make the lead chloride, and that's called the net ionic equation. So in our equation, the spectator ions would be the sodium and the nitrate. They're both the spectator ions. And it's the ions that don't make the precipitate. Any questions on this before we go on? Okay. All right, when solutions of silver nitrate and sodium chloride are mixed, a white solid forms. Write the ionic and the net ionic equations for the reactions. So I'm going to let you all work on it for a minute, and then we'll. Okay. And it has to be balanced. In this case, it's all one mole of each, so there's no coefficients. Once you've written down this equation, your next step is to decide if either one of these is insoluble. And if you look at the rules, you're going to see that this silver chloride is insoluble and sodium nitrate is soluble. That's when you write your complete ionic equation, and in your complete ionic equation, you're going to show the silver chloride in the end associated form, because you first decided that that's your insoluble product. There might be some ion equation that you will run into where you have both products are insoluble, then you're not going to write either one of them as in the ionic form. Or you might have equations where both of them are soluble, so you will have nothing in the combined form like the silver chloride. Okay, now what about the net ionic? Net ionic is going to show the formation of the insoluble product. They start out as aqueous ions because they're both part of soluble compounds, and then you're going to end up making the silver chloride in the solid form. I think we've seen something like this before, right? When we did the electrolyte lab? No? Okay. So that's and then notice you're able to cancel out the spectator ions from both sides, and then silver and chloride combine to give you the net ionic equation. And we've seen this reaction before. Two clear solutions, silver nitrate and sodium chloride are both clear. Mix them up and you got the milky precipitate, remember? And then that settles down at the bottom, and that's your insoluble salt. Okay. We are going to find many to do in the book, so let's go there. All right, so we're going to calculate the concentrations of solutions in this last PowerPoint, or maybe last PowerPoint. We'll probably do one more after this for this chapter. And use concentration units to calculate the amount of solute or solution. The concentration of a solution is the amount of solute dissolved in a specific amount of solution. So the concentration would be equal to amount of solute divided by the amount of solution. And there's 3 or 4 different ways to express concentration. The first one of which was called mass percent, where you have mass of solute over mass of solution. That's why you have M over M, describes the mass in grams of solute per 100 grams of solution. The mass of the solution in grams goes at the bottom. So to get the mass of the solution, you need to add the mass of the solute plus the mass of the solvent. So mass percent equals to mass of solute in grams divided by mass of solution times 100 gives you the percentage. And you want to be sure you write these formulas correctly and know them correctly, because they're similar to each other. And for the mass percent, you need the mass of solute over mass of solution. And this is the first one. Suppose we prepared a solution by mixing 8 grams of potassium chloride. The solute here is potassium chloride, and you dissolve it in 42 grams of water. Water is a solvent. When water is added to 8 grams of KCl, potassium chloride, to form 50 grams of potassium chloride solution, the mass percent would end up being 16% M over M, because you have 8 grams of solute, and then To get the mass of the solution, you would add the mass of the potassium chloride and the mass of the water put together would give you the 50 grams of solution. And times 100 gives you 16%. Any questions? Okay. A solution is prepared by mixing 15 grams of sodium carbonate and 235 grams of water. Calculate the mass percent of the solution. What would you do? Divide the 15 by the what? Huh? 250, because it's going to be 235 plus the mass of the solute, which is 15, and then multiply by 100. Right there. So 6% sodium carbonate. Right, volume percent V over V. Now you're going to have volume of solute and volume of solution at the bottom. So the volume of the solute in milliliters or liters, and then the volume of the solution in the same units as the solute would go at the bottom as the denominator and times 100. A bottle of vanilla extract is 35% alcohol. This means the bottle contains 35 milliliter of ethanol in 100 ml of the solution. So the 100 ml would include what? The 35 ml of the ethanol. And what? It's the volume of the solution, so it would contain the ethanol or the alcohol as well as the solution, the vanilla solution. A bottle contains 78 milliliters of lemon extract solution. If the solution contains 62 milliliters of alcohol, what is the volume percent of the alcohol in the extract solution? The 62 ml of alcohol would go at the top, and then at the bottom it would be the 78 ml of the extract solution, which contains 62 ml of alcohol. So 62 over 78 times 100. And this is volume percent, where you're going to be having the volume of the solute and the volume of the solution at the bottom. And notice that both the equations that we just looked, both the formulas had solute at the top and solution at the bottom, whether it was mass of the solution or it was volume of the solution. It did not have the solvent at the as a denominator. Mass over volume percent, M over V, describes the mass of solute in grams per 100 ml of solution. The solute is going to go in grams, and the solution volume is going to be in milliliters. So you need the mass of the solute, but the denominator is going to be the volume of the solution. This is essentially you dissolving a solid in a liquid, most times. All right, mass over volume percent is widely used in hospitals and pharmacies for preparation of medicines and intravenous solutions. A 5% mass over volume solution of glucose would contain 5 grams of glucose in exactly 100 ml of solution, because 5 over 100 times 100 would give you the 5%. Has a combined volume of glucose and water to make 100 ml solution. So you would prepare it by, for example, if you wanted to prepare it in this volumetric flask, right there, for example, you would take 5 grams of, what was the substance again? Glucose? Yeah. You would take 5 grams of glucose in here, and then you would add water to the 100 ml mark. That way, the glucose powder and the water together gave you a volume of 100 ml, because at the bottom you need to put down as the denominator the volume of the solution. Okay. That's the one we were on, right? Okay. All right, molarity. Now, molarity is the one that's most commonly used in chemistry. Is used when working with solutions. The moles of solute per 1 liter of solution is called molarity. If you remember in our lab, we have been looking at solutions. Some of them may have said 6M HCl or 6M nitric acid. That's the molarity of the solution, and molarity is the strength of the solution. So molarity is equal to the moles of solute that you have in there divided by the liters of the solution. So this is our fourth way of expressing concentration. Molarity gives you the strength of the solution, meaning how strong is your solution. Is it dilute or is it concentrated? The more number of moles you have, of course, you have a stronger or a more concentrated solution. and moles over liters of solution. So the volume is the denominator here, and the volume has to be in liters. For example, if 1 mole of sodium chloride is dissolved in enough water to make 1 liter, then the concentration of the solution would be a 1m solution. Molarity is moles per liter. 1 mole of sodium chloride over 1 liter solution would give you 1m NaCl. 1 over 1 is equal to 1. So the formula here is moles over liters is molarity. What's the molarity of 87.7 grams of sodium chloride in 0.250 liters? What did we say the formula was for molarity? Moles divided by liters. The volume has to be in liter. It cannot be in any other unit. So molarity equals to moles divided by volume in liters. What do we have over there? We have the volume in liters, so we have that part, but we don't have the moles. So can we go to moles, starting with the 87.7 grams of NaCl? Yes, right? You can, and using the molar mass of sodium chloride, we would go to moles of sodium chloride. There's 1 mole. Grams and grams cancel out. 87.7 divided by the 58.5. Oh. 1.499, which is 1.5 moles. Right? So moles, and we need the volume to go in liters, so it's going to be 0.25 liters. It's going to be a 6m solution. 5.99, which is equal to 6. Any questions on this? So what did they do here? You would make these solutions in a volumetric flask where you would put in 87.7 grams of NaCl, which is equal to 1.5 moles, and then add water to the 0.25 liter mark. Or any questions on this, on finding molarity? Now notice with the molarity formula, you have 3 variables, and you can be given any 2 of those 3 and be asked to find the third one. Just like, well, here they gave us the moles and the volume, which is the most common way. But they could give you molarity and ask you to find volume, or give you molarity and volume and ask you to find moles. All right, so let's look at the summary of types of concentration expressions and their units. Mass percent is solute is going to be in grams, and solution is also, you need the mass of the solution and the solute. For volume percent, you need the volume of the solute and the volume of the solution. And then for mass over volume percent, you need mass of solute and volume of solution. And then for molarity, you need moles and liters. Okay, conversion factors from percent concentrations. 15% m over m KCl potassium chloride solution would mean 15 grams of potassium chloride in 100 grams of potassium chloride solution. So which is 15 grams of KCl over 100 grams of solution. That would be the conversion factor that actually comes out of that solution. And you can flip the conversion factor too, depending on how you want to use it. 12% ethanol solution would be 12 milliliter of ethanol in 100 ml of ethanol solution. 12 milliliters of ethanol goes at the top, 100 ml solution goes at the bottom. 5% mass over volume glucose solution would be 5 grams of glucose in 100 ml of glucose solution. And then that conversion factor can also be flipped. 6 moles of HCl, hydrochloric acid, in 1 liter of solution is also a conversion factor. So any of this information can become a conversion factor. A typical antibiotic ointment Neosporin is 3.5% neomycin solution. How many grams of neomycin are in a tube containing 64 grams of ointment? So neomycin here is the antibiotic, but you don't apply the antibiotic directly. It's going to be dissolved in some base. So what this is saying is that you have 3.5% of the antibiotic in the solution. The ointment is called Neosporin, and only 3.5% of it is the actual antibiotic neomycin. So 3.5, it's mass over mass, so 3.5 grams out of 100 grams is what? Neomycin, right? 3.5 grams of neomycin in 100 grams of ointment. This is the conversion factor. This is the information that you can get from the 3.5% M over M neomycin solution information. And then it's saying how many grams of neomycin would there be in a tube containing 64 grams of ointment. So you start with the 64 grams of ointment, and you would use this conversion factor. There's 3.5 grams of neomycin in 100 grams of ointment.
So where'd you get the 100 grams from?
Based on the information that's given, the 3.5% neomycin solution means, since it's 3.5% mass over mass, means it's the solute over the solution. The mass of the solute, that's the solute there. This is the solvent, this is the solution. So let's put that over there. So remember, this is a mass percent problem, where you put the mass of the solute goes at the top, and the mass of the solution goes at the bottom. And the solution here is the Neosporin, because the antibiotic has to be in some base. And the total mass of the ointment is 100 grams. 3.5 grams of it is going to be the neomycin. If you have 64 grams of the ointment, then you can use the conversion factor, and this cancels. And 64 times 3.5 will give you the mass of neomycin that's going to be in there. So let's go and look at it. There. So you want to make sure you remember what the formula was. Like for mass percent is mass of solute over mass of solution, and then this part here tells you also that it's mass over mass, and it's always mass of solute over, or volume of solute over, it's solute over solution. It can be mass of solute and mass of solution, volume of solute and volume of solution, or it can be mass of solute and volume of solution. That's M over V. That's the third kind that we did. Okay, let's look at this now. How many grams of potassium chloride are needed to prepare 0.125 liters of a 0.720 molar potassium chloride solution? What do we need here, and what do we...
Grams.
We want to find grams eventually. Before we can get to grams, what are we going to need to find? Looking at this information that's given, the molarity and the liters, what can we find? You have molarity and liters, and the formula said what? Before we can get to grams, we need to find moles, and we can't find moles because we have this formula now. Molarity is equals to moles over liters. We have the molarity. We have this part 0.72. We have the liters 0.125. Right? That's your x moles. So you can solve for your x, which means multiplying both sides by 0.125. This will give you the moles. Once you have the moles, then you can use the molar mass of potassium chloride and go to grams. So, well, they did it all in one step. We could do it all in one step too. However, basically that's the breakdown, where these two numbers multiplied will give you 0.125 times 0.720 is 0.09 moles. And then you're going to say 1 mole is equal to, I think potassium is 39.
74.55.
Okay. So 74.55 grams times 0.09. Oh. $6.71. Any questions on this? So you can be given any two of the three variables and asked to solve for the fourth one. No questions or what? No questions, everybody? Or is it a lot for one day?